Hello, in this video I am going to talk about estimating, specifically using sample proportions to estimate population proportions. In a previous video I talked about the sampling distribution of the proportion and why the sample proportion is a good estimator since it is unbiased and consistent. So the sample proportion is a good estimator of the population proportion, but that is just a point estimate. A point estimate is a single numerical value. The question becomes, how good is this point estimate? We answer the question of how good the point estimate is by constructing a confidence interval. So a confidence interval is what we call an interval estimate because it consists of a range of values. We're going to basically construct a range of values in which the sample proportion is the center of that range. But in order to do this, we need what's called a level of confidence. And this level of confidence is going to define the likely values in the distribution. Recall that the sampling distribution for proportions is normally distributed. So we have a normal distribution of the sample proportions p hat, where the center of the distribution is the population proportion p. We want a range of values that will capture the true p with a likelihood of 95%. We can use other likely values or likelihoods, but 95% is the most common. So that means when we look at a distribution of sample proportions, the middle 95% are what we consider the likely values. So the middle 95% are the likely values. That leaves the bottom 2.5%, and the upper 2.5% are considered the unlikely values. So what that means is if you are to compute a sample proportion and then you create a 95% confidence interval around it, you will have a 95% chance that your method actually worked and you captured the true proportion, right? Because if you have a 95% chance that the sample proportion you compute is in this middle 95%. The least likely scenario is you're barely in that 95%. So you want to be able to create an interval around your sample value so that it captures the true proportion. In order to do that, what we're going to do is take our sample proportion and add and subtract to it this distance right here, and that distance there is referred to as the margin of error. All right, so that's the key. That is what we're going to be doing here. All right, so let's talk more about that margin of error. So notice here, the level of confidence defines the likely values, which I was showing you in the picture. So our level of confidence defines likely, and we are going to use 95% because that's the most common. The middle 95% of a normal distribution is within 2 standard deviations of the mean. That was according to the empirical rule. So when we have our normal distribution here, right, this middle 95%, this middle 95% is 2 standard deviations from the mean. Now the mean here is the true proportion. And so 2 standard deviations would be this distance here. Okay, that's 2 standard deviations. 2 standard deviations has a z-score of approximately 2, but when you go to 2 decimal places, it's actually 1.96. So this here is 1.96 standard deviations from the mean, p, and right here is also 1.96 standard deviations from the mean. So we want to add and subtract a value that's 1.96 standard deviations from the mean. And that value, as I mentioned, is the margin of error. Okay, so for the margin of error, to compute the margin of error, we need to take this, that 1.96, or if we're still rounding, the 2 standard deviations from the mean, but then we have to multiply it by the value of the standard deviation for the sampling distribution, which remember is called the standard error. So to 2 decimal places, the margin of error will be 1.96 times the standard error. So that 1.96 is the z-score because we're defining likely as the middle 95%, and then the standard error we'll have to compute based on our data. Recall that the standard error is here defined as the square root of p times 1 minus p divided by n. Now you probably realize, wait a minute here, p is the population parameter that defines the middle. We don't even know that. We are estimating that with the sample proportion p hat. So how can we compute the standard error if we don't know p? Well, easy. Instead of p, we'll approximate it by using, you said it, p hat. So we compute this with p hat in place of the p's, right? We're going to use the p hat. So now let's again look at this. So what we have here is the margin of error, 1.96 times the standard error. We saw how to compute the standard error by doing the square root of p hat times 1 minus p hat over n. And then to get the left endpoint of our confidence interval, we will subtract the margin of error from p hat. And to get the right endpoint of the interval, we will add that margin of error to p hat. So the 95% confidence interval will be between p hat minus the margin of error and p hat plus the margin of error. So now let's look at an example. So here we have an example where we have a random sample of 1,228 medical malpractice suits, and it was found that 856 of them were later dropped or dismissed. So we're going to start off by finding the point estimate of the proportion of medical malpractice suits. So we're finding the sample proportion here. What we're looking for is, in fact, p hat. Recall that p hat is the number of successes divided by the sample size, because it's the same thing as a relative frequency. So to compute p hat, we simply take the number of successes, which in this case is the 856, and we're going to divide that by the sample size, which is the 1,228. So we have 856 divided by 1,228. And here is our sample proportion of 0.69707. There is our sample proportion, or the p hat. Now we're going to use that p hat to find an estimate of the standard error. So equals SQRT, that's the function for square root. And so we need the square root of our p hat times, open parentheses, 1 minus the p hat, close parentheses, divided by the sample size of 1,228, closed parentheses, and here we get our standard error, or our estimate of the standard error, as 0.01311. That's a pretty good estimate. Now, let's find out what the margin of error will be for the 95% confidence interval. So remember, the margin of error for a 95% confidence interval is 1.96 times the standard error. So whenever we're working with a 95% confidence interval, the z-score is approximately 2, but more precisely 1.96 times the standard error to give us the margin of error. So in this problem, we see that the margin of error is a little bit more than 2.5%. A little bit more than 2.5%. That's not bad. We like to keep it 3% or less, so that's all right. So that's a pretty decent margin of error. And now to find the confidence interval, we're going to add and subtract that margin of error to the sample proportion p hat. So here's p hat minus the margin of error, which gives us a 0.6731 or 0.67137 as the left endpoint of our interval. And then the right endpoint will be the sample proportion plus the margin of error, and that gives us 0.72277. So these are the endpoints of the 95% confidence interval. How is that interpreted? It is interpreted like this. We say now that we are 95% confident that the population proportion, in this case it would be the population proportion of malpractice suits that are dropped or dismissed, is between, and I'm going to convert these to percentages, 67% and 72%. So this then is the interpretation. We are 95% confident that the population proportion is in between 67% and 72%. Now, let's be a little bit precise on what we mean by 95% confident. This is not saying that there is a 95% chance that the population proportion is between 67% and 72%, although that might be feeling like what it's saying. What it's saying is that 95% of the time, what we did would capture the true value. So we're confident there's a 95% chance that our method was good and we had a good sample, and that we actually know that the population proportion is between 67 and 72. So that 95% confidence is the confidence in our method. Because remember that what that percentage is we're looking at the curve here, and 95% of the sample proportions are here, right? And we created that interval by thinking that we could just barely be in here, right? This could be our p hat, and it's still in the likely area. And so to capture the true value, all right, we created an interval around it that was just big enough to get over basically half of this here, and that's how we got the margin of error. And we say that margin of error is the maximum likely difference between the theoretical and our sample statistic. That's the maximum likely difference. All right. So this method is based on the fact that there's a 95% chance that we actually got a likely sample and a likely value for a sample proportion. It's always possible that we got something in one of the tails, in which case we would have had an unusual sample. And so when we created our interval around an unusual sample, so let's say we got something here and this was our p hat, we create that interval using the same margin of error around it, and notice because it was an unlikely sample, we don't actually capture the true value in there. So there's a 95% chance that we get a likely value, but then there's still that 5% chance that we get a value that was either too small or too big and therefore unlikely, so that our interval did not capture the true value. So 95% confident is that we have a 95% chance we actually got a representative or likely sample so that our interval actually captures that true population proportion. All right, so let's go a little bit further now and see how we can use that result. So here in number 6, does the confidence interval support the claim that more than 65% of medical malpractice suits are dropped or dismissed? Okay, so a claim of more than 65%. When we look at this interval, we see, yeah, everything in this interval is indeed greater than 65 because the smallest value according to the interval is 67. So then the answer is yes. The interval supports the claim since all values in the interval are greater than 65%. All right, so that's how we use the confidence interval. Let's go ahead and look at another example that goes back to data over here that I talked about in another video where I have the frequency of vehicle types in their sales. Now here we have all these different categories, but down here in number 5, I decided to focus on only the compact sales. So we just focus on the compact sales. All right, we want to find the point estimate for the proportion of vehicle sales that were compacts. So we go up and we look at our data, and we see that for compacts, there were 28 out of the 180 sales were for compacts. So let's go down here, and the point estimate then is going to be that 28 divided by the 180, and that will give us our point estimate or the sample proportion. So this here is p hat. We are going to use that p hat to now estimate the standard error, which is the square root of p hat times parentheses 1 minus p hat closed parentheses divided by the sample size, which was 180 close parentheses. And so we have a estimate of the standard error as 0.027. Now for the margin of error, we're going to again make a 95% confidence interval. So that means we are going to multiply our standard error by 1.96. So 1.96 times the standard error. And this time we get a margin of error of 5.3%. So this is a bit bigger than is normally desired. If we wanted a better estimate, we would want a bigger sample size, right? Because remember, in the formula, in the formula here, we divided by the sample size. And so the bigger the sample size, the smaller the standard error. And of course, the smaller the standard error, the smaller the margin of error, since the margin of error is approximately twice the standard error. But working with this one then, we can get our confidence interval. So remember, it's your p hat minus your margin of error for your lower limit. And for the upper limit, it's your p hat plus the margin of error. So we see then that we are 95% confident that the population proportion of cars sold that are compacts is between, let's see, 10.3% and 20.85%. This time I gave more decimals. I could have just said 10% and 21%. It just depends on how many decimals you feel like giving here. So we're confident the population proportion is between 10.3 and 20.85%. All right, so 95% of the time, our method will give us a correct solution, meaning it'll give us an interval that actually captured the true value. So now this question 10, does the interval support the claim that less than 20% of vehicle sales are compacts? Well, let's see. When we look at this interval, we see that the upper value is bigger than 20%, just barely, but it's like 21%. In order for this to be true, all values in the interval would have to be less than 20%. So actually, we cannot say it supports. We have to say no, since some values in the interval are greater than 20%. All right, so thank you for watching this video, and I hope that makes it clear how you can use Excel and its computations to find confidence intervals. Thank you for watching.